Mastrolia. He will tell us about intersection theory for fundamental interactions, or about mathematical method for scattering amplitude to modern scientific calculus. Paolo, please, 1 hour.
Okay, thank you very much to Luca for the invitation, and to Irina for the presentation. It's a real pleasure to be able to present and to share to this audience what could be as a summary of our finding, our recent finding in the development of the methods to compute generically multi-loop Feynman integrals from scattering amplitudes, and actually out of it we were able also to derive properties which in general are of more wider application and can be applied to several contexts in scientific calculus. So let me start simply by saying that usually the goals of theoretical physicists is to model nature by understanding how systems evolve, and in particular in describing how promptly a quantity can change with respect to the change in another or more quantities. And what we do in order to control this evolution is technically to provide differential equations. Now, alternatively, as a physicist, we also like to study, to investigate relations among observables that then turn into relations among functions. And actually, although during classes we learn or we deal with these two types of equation in a different way, I'd like to propose to look at them in a way that looks similar, because if we simply recast, for instance, the n-order differential, the derivative with respect to the other, then both these relations look like a decomposition formula. Namely, we have something on the left-hand side, which is written as a linear combination of objects that appear on the right-hand side. So this simple rewriting, or this simple change of perspective actually allow us to study properties of scattering amplitudes or of Feynman integrals, we could say, that are the building block of scattering amplitudes, that have been in the past 2 decades extremely important for the precision physics, precision program at colliders, but also to study more fundamental property and the geometrical property of quantum field theory, as well as to export the technical and the mathematical methods we developed for collider physics, in particular for particle scattering, beyond collider. And 2 of the most recent application in this area are application to the description of merging system in the gravitational wave generation, as well as to investigate cosmological correlators. So let me start with a basic definition of what a Feynman integral in dimensional regularization looks like. So we have generically dimensional regulated integral associated to diagrams that have a certain number of external legs corresponding to particle momenta and to a certain number of loops corresponding to integration momenta, that are generically, so in full generality, even without referring to any theory, they are inverse power essentially of denominator, or products of denominators if you allow for negative exponent. And they are characterized clearly by the picture associated to the diagram containing a given number of loops, a given number of external legs. And generically, one can build out of the scalar product one can build a given number of scalar product between external momenta and loop momenta, here reproduced by this formula. The denominators that I'm concerned with are the usual quadratic denominators of a Feynman propagator, in which essentially they are quadratic in momenta and eventually in the mass. Now, there have been since dimensional regularization has been introduced, there have been a number of tools and techniques that have been proposed to compute Feynman integral. Okay, on one side we have direct multivariate evaluation, and sometimes when these become too prohibitive, if the diagram is too involved, or if the masses of the particle and the scales associated to the diagram start to grow, then usually one opt for different techniques that can rely on the existence of relation known as integration by parts identities, or the most recent method based on unitarity. And sometimes, instead of addressing the direct calculation of the integral, one prefers to use integration by parts identities or other relation to write difference equation or differential equation, of which the integral is a solution. So instead of computing directly an integral, one solves an associated differential equation. And there have been, in particular for collider physics, interesting development based on the so-called integrand decomposition that mathematicians can look at or consider as just coming from polynomial division. So the focus of my talk is on some new technology that somehow binds together concepts that were proposed in these different areas. So let me first start by a very well established method for Feynman integral, which is the existence of a relation between Feynman integrals owing to the vanishing of the integral of a total divergence for arbitrary number of dimensions. Okay, this is like the generalization of Gauss law. And now, owing to this vanishing equation, indeed, it is possible to build an infinite towers of relation for Feynman integral associated to a given diagram, which essentially connects integrals that have the same number of denominator, but with the dancing with different powers. Okay, so we can build this larger number of system of equation, and then in the past few years, people have developed a very nice idea to solve this system of equation, which are over-constrained system of equation, in order to express integrals of Feynman integral in what can be considered a basis of irreducible function. And this basis that appear on the right-hand side of the equation is generically called the basis of master integrals. So in this picture, all the integrals belonging to a scattering amplitude then can be first decomposed into a basis, so this basis of master integral, and then the same relation can be used to build differential equations or difference equation solved by the master integral. And therefore, if one is able to solve this differential equation, one finds the expression to replace the basis and get finally the quantity of interest, namely the scattering amplitudes. Now, as said, the existence of this relation among integrals is it's extremely interesting from the algebraic point of view. A different way of determining the coefficient of this what can be considered linear decomposition could be, for instance, accessed through the use of unitarity ideas. In the unitarity case, what happens is that the original integral or the denominator of the original integral are replaced by delta functions, and what happens is that in replacing all possible denominators of the integral, one can build also a triangular system of equation in which the relation that originally are expected for the complete integrals are simpler, okay, for the cut integrals. And in particular, in the cut integrals, there appear less terms than the one in the original equation. But solving this system, this triangular system, is also useful to determine the coefficient that multiply the cut integrals, which are identical to the coefficient of the original decomposition. And so unitarity inspired idea have been extremely useful in order to solve simpler set of equations to extract the same information as in the original decomposition. And the decomposition can be also improved if one combines the ideas of generalized unitarity with the idea of integrand decomposition, namely considering a generalized partial fraction in between the numerator of a diagram and its denominators. This technology has been indeed extremely important for what has become the next to leading order revolution in the evaluation of processes at one loop that have been extremely important for the analysis of LHC physics in the past decade. So allow me also to say that the ideas that I'd like to discuss today could be elementary expressed as a kind of generalization of the discrete Fourier transform. As we know, if we have a polynomial in a given a polynomial of a certain degree, here I'm just indicating one variable, okay, it is possible to extract the coefficient of a linear of this in front of each monomial by projection, okay? And the projection formula that we probably everybody in the audience know is it involves technically a double sum, okay? A double sum from which one can extract directly the coefficient of the decomposition. Now, what I would like to propose is to look at this formula in just a different way. Essentially, since the sampling or the evaluation of the variable running in the sum technically live on a circle, allow me to write this external sum like a kind of by abuse of notation with this O plus sum, okay, where the circle recall us that the variable, the summation variable lives on a circle. Now, in the past, I also proposed a method for the evaluation of the double cut of scattering amplitude, which was used extremely, it was important to extract the coefficient of two-point function out of the amplitude, and also this formula based on generalized Cauchy-Pompeiu formula for non-homomorphic function. Essentially, it's a double integral that exploits Cauchy theorem. Okay, so these ideas came into the game in order to study the property of Feynman integral within an algebraic approach that from which it is possible really to characterize in an ambiguous way a vector space structure of not only Feynman integral, but also of generalized Euler-Mellin or GKZ, Gelfand-Kapranov-Zhelewski function, also known as a homoto-hypergeometric integral, that mathematicians like to call twisted period integral. So whatever we learned from Feynman integrals calculus could be easily exported to this wider class of function that appears in many branches, not only of physics and mathematics, but also statistics and eventually also finance and different scientific areas. So the idea that I will elaborate on in the rest of the talk will be based on the theory of the Rham co-homology group, and I will mention a few methods that we introduced to compute the so-called intersection number, and then recall a few applications both in mathematics and in physics.
Paolo, I have
yes.
a question. Maybe you will say this soon.
Yes.
But as you said, basically you can really talk in terms of the language of vector spaces, where you have a basis of these diagrams. Yes. So you can also define, I guess, scalar products between these elements of the basis and some orthogonality and
Absolutely, that's correct. Indeed, you anticipated exactly these slides. Namely, really from the basic point of view, in order really to build a vector space, right? Our idea is to decompose our integral I in terms of master integral here I call J, and we need, of course, to sum as many elements as the number, the dimension of this vector space. If we are able to do this, then it means also that we should be able to provide an inner product between integrals in order, which works for us like a scalar product, so to extract the coefficient by projection, as well as to write a resolution identity equation. And in order, what I wrote up to here is very generic, but what we need to do for Feynman integral in this class of twisted period integral is to provide what is the definition of the vector space and what is the scalar product between the integrals. So I have to say that in order to arrive to define both notions, so the dimension of the vector space and the scalar product, allow me to propose what mathematicians do is to consider the integral, okay, it generically contains an integrand and there is a special domain to be written generically in the case of Feynman integral as the product of a multivalued function. So the integrand can be written as the product of a multivalued function that regulates the integrand and a differential form. And then the idea is that these two pieces of the integral really can be seen as belonging to two different isomorphic vector space. So we have the space of the domain, of the integration domain, which is associated, which is bound, which is related to the multivalued function, and the space of differential form. And the integral can be really seen as a map, as a pairing between these two spaces. If we accept this vision, right, the property that we ask the multivalued function is to vanish at the boundaries of the integration domain. And owing to this requirement, then we can be sure that the integral of a total differential vanishes, or alternatively that indeed via Stokes theorem the full integral vanish at the boundary. So these two ways of writing this zero are indeed the dawn, are the origin of the existence of the integration by parts identities. Okay, the integration by parts identities I wrote before are more resembling the vanishing of a total differential, but again, Stokes theorem allow us to introduce a dual interpretation of this vanishing. And that's the basic picture underpinning intersection theory. So mathematicians define then the twisted period integral as the pairing of these two objects. So we have this part of the integral which characterized what's known as twisted cycle, and the differential form is usually defined twisted cocycle with the property, that the twist, the function u, is vanishing at the boundary. And let me soon say which type of integral belongs to this type of, which family of integral belong to this function, to this set of twisted integral. Well, gamma functions or Euler beta function, the Gauss hypergeometric function and its generalization, they all can be can be interpreted in this formalism, where the u function, the twist, is, as we are going to say, what characterizes the integral. And so our primary goal was to recognize that also Feynman integrals may admit this structure. So where does what are the basic elements to apply the Rham theory to this type of integrals? Well, the vanishing of a total differential, okay, here I'm writing the equation we saw before schematically, implies the existence of a covariant derivative, this nabla omega, where omega is the total differential of the logarithm of the twist. So in this scenario, the logarithm of u, the logarithm of the twist, plays the role of a Morse function. Okay, and as soon as I have an integral, of course, the vanishing of this total differential implies the existence of an invariance of the integral, namely an integral remain invariance if I add to the integrand a term which is controlled by this nabla omega operator. So with Stokes' theorem, this also can be seen as the invariance of the integral if I shift my integration domain by a boundary term that clearly does not encircle, does not include any singularity. Okay, so I have these two visions to study the integral invariance, either by shifting the integrand or by shifting the integration domain. And also, anytime that I define an integral as the product from the product of u and a differential form as a bonus relation, I also can introduce dual integral simply by sending u in u inverse. And in this case, those dual integral allow me to write a dual covariant derivative, which I obtain from the covariant derivative simply by sending omega in minus omega. So what happens essentially is that within this theory, within this approach, I am able to identify four equivalence classes that are called the co-homology groups, and it's dual. In particular, the invariance of the differential form by shifting so under shift allow me to define the cohomology group of closed form modulo exact form, and invariance under the deformation of the domain allow me to define the so-called homology group. And this duality of sending u into u inverse, omega in minus omega, it gives me the opportunity to define other two mirror space of the former two. Also of closed formula or closed form modulo exact form, as well as of m cycles modulo boundaries. And so I have four spaces from which I can take elements, so I can define left form, I can find right form, they belong to the co-homology group, as well as I can define right contour and left contour as elements of the homology and dual homology group. And I can start forming pairing among them. So if I pair a left form with a right contour, indeed, I generate my original integral. If I pair instead the dual form and dual contour, then I form dual integrals, where the twist now appears as characterized by u inverse. And then I can start pairing contour. What is the pairing of the contour? Well, the pairing of the contour represents what's known as homology intersection number, which is a generalization of Gauss linking number or winding number. So it's really it measures, it counts the number of times a boundary winds around the other. And similarly, or in a dual fashion, we can introduce intersection number between forms. I don't have a visualization of these, but it is indeed a possible natural pairing. And as I'm going to elaborate on in the rest of the talk, this is the intersection number are the key object, the key element to exploit the algebra or the vector space algebra of Feynman integrals. In particular, so these four spaces are isomorphic, and the dimension of the homology and homology group, it's essentially what is found to correspond to the number of master integral. In fact, imagine that we are able to compute that the theory give us this number ab initio, then I can introduce basis of form and dual basis, and so I can define the identity resolution as any identity resolution in a vector space where the intersection matrix between basis and dual basis not necessarily is orthogonal. If it is orthogonal, then here I would get a Kronecker delta ij, and so this identity matrix then look like the identity matrix operator in quantum mechanics, right? But in case these differential form are not orthogonal to each other, then generically I have this inverse connection matrix. And similarly, I can write the identity operator in the homology space using as a basis not the differential form, but rather the contour of integration, okay? Elements taken from homology and dual cohomology. And so I can use this identity resolution to write my linear decomposition. In fact, if our problem was the decomposition of the integral I represented by generic integrand phi left, by differential form phi left, in terms of a master integral basis, I can reproduce this formula starting from a form, so in my cohomology group, multiplying by the unit operator, and then out of the unit operator that I substitute here, I can simply recognize, okay, that this building block here is the coefficient Ci that multiplies the basic element. Okay, so Ci, which is the coefficient of the master integral composition, in this framework can be completely determined in terms of intersection number between forms. Okay, what's important is that on this form now I have intersection number between the form that I want to decompose, phi left, and the dual basis, as well as the inverse matrix element C, which is the intersection number between, which is formed, whose elements are the intersection number among basis and dual basis. So in this context, we propose that the decomposition of integrals can be completely controlled by intersection number. This is the first new concept that we introduced. Nicely, we can derive also a higher order relation, which generalized the so-called Riemann bilinear relation. I don't want to enter in these. I leave the slides for question or for interested readers. I just want to tell you that in the case of non-twisted integral, Riemann proposed already the existence of the intersection number, and one can try to recast this very well-known identity in a form that looks like the one I showed you before. And in particular, indeed, Cho and Matsumoto in 1995 proposed the extension of this formula, which can be understood like the insertion of the identity operator in between the intersection number, either for form or for contours. Okay, one gets this quadratic relation because they involve the product of integral and dual integrals. So for the vector space of Feynman integral, then now we have a full characterization. So let me first say that for people that also in the audience are familiar with the integration by parts identities, in the context of Feynman integral calculus, the number of master integral is still found as a posteriori concept. Namely, people usually first generate this large system of equation, then solve the system, and then one counts the irreducible term that have not been decomposed. So, and then one determine or identify the master integral. In this formalism, in this new formalism based on the Rham cohomology, now the number of master integral can be computed as an a priori concept. And in our work, we have essentially used the method suggested by Lee and Pomeranski, counting the number of critical points of the logarithmic function u, okay, as a Morse function. But there are several methods that can be found also in differential geometry associated which associates the dimension of the cohomology group to the Euler characteristics, or even in algebraic geometry to dimensions of quotient space in ideal saturation, or in algebraic statistics. Now the number of master linear can be computed as the mixed volume of Newton polynomial, as well as in terms of the holonomic rag of GKZ system. So what's nice of this new point of view is that there is a pretty very well defined mathematical framework which can provide the algebraic property of the integrals coming out from geometry. And now, how Feynman integral then can be recognized to belong to this family of integrals? So the idea came to us when we looked at Feynman integrals, generically written as the when one identify the integrand to these two basic elements, so the twist and the differential form. So the twist can be generically represented as a graph polynomial raised to a non-integer power, here gamma, and the differential form, as we are going to see in a moment, is just obtained by the product of the denominator. In fact, Bajkov representation is what was for us the proper way of identifying this structure. In particular, in Bajkov representation, is based on a change of variable, namely where the denominator becomes the integration variable. So you switch from the component of the loop momentum to the denominator, and in this form, then the u function is the Bajkov polynomial, or if you wish, the grand determinant that one can build between the external momenta and the loop momenta. So very nicely, in this form, Feynman integral can be recognized to have the twisted period integral representation. And so once one builds the Bajkov polynomial, then it is possible to write omega, namely the differential logarithm of this polynomial, counting and identifying zeros and poles, so that the dimension of the cohomology group associated to this integral basis is nothing but the number of critical points, as Morse theory suggests, which for us means by counting the number of the solution of a zero-dimensional system built in terms of the partial derivative of the omega differential form. So there is now, any time that one looks at an integral, in particular if it is a twisted period integral, one can identify the twist and compute automatically the dimension of the cohomology group, so you know how many master integral you should expect, namely how many elements of generators the basis should be composed from. And so that then one can proceed in choosing almost arbitrarily this basis of form and dual basis, so to decompose any integral of this problem in terms of the chosen basis. Again, the coefficients are written in terms of intersection number. So let me show what are the special application, a few special application of this formalism. Okay, so now we have a method, a very powerful method, given an integral, or better, a family of integral, one can directly associate to this integral the existence of a geometric picture characterized by the twist u, by the eventually this polynomial here of this function, and out of this function one can, the critical point of this function allow us to determine what is the dimension of the cohomology group. So a first application is to derive I don't pretend to go to the step, but allow me to say that in a similar way in which we built the linear decomposition identity, now we can we can decompose the derivative of the master integral. And so the derivative of master integral can be expressed again in terms of master integral, and the coefficient matrix in front of it, it's also a generalized connection matrix that allow us to write a Pfaffian system solved by the master integral. So we not only can decompose an integral in terms of master integral, but this formalism, again using intersection number, allow us to compute directly the entries of the system obeyed, or differential system obeyed by the master integral. Or in particular, we can build higher order differential equation satisfied by each master integral in a very simple way, because in this formalism, building an higher order differential equation simply means for us a change of basis. So instead of choosing randomly our forms in which we want to decompose the basis, we can take one master integral and its derivative, and then decompose one derivative, one extra derivative in terms of them. Okay? This decomposition formula corresponds to an higher order differential equation for the master integral. And in a similar way, we can build a finite difference equation for the master integral, associated this time to the so-called dimensional shift equation for the master integral. These results, I have to say, were already known in the context of Feynman integral in momentum space, and here we propose a new and straightforward way to derive them directly in terms of intersection number. Finally, this was instead less known to people working in Feynman integrals calculus. The existence of differential equation for master forms and dual master forms allow also to express a differential equation for the matrix intersection matrix of intersection number. Namely, the matrix C is also a solution of a differential equation, which is known as a secondary equation. This was a result that was known in differential geometry by Matsubara, Heo, and Takayama. So let me, up to now, I have only been able to, I hope that I've been able to communicate the fact that intersection number rules or are the answer to what Luca asked before, or to the question of what is the inner product between integrals. So the inner product between integrals is the intersection number. And owing to the intersection number, we are able to build a decomposition formula or differential equation or difference equation. But up to now, I did not tell you how to compute intersection number. And that's what I'd like to do in the next few minutes. So
maybe, Pierpaolo, if I can ask again
yes.
Another question. So just to understand, maybe with an example, for
Yes.
my understanding at least.
Yes.
Let's suppose we take 5 to the 4 theory.
Okay.
And we consider the simplest case, like just 2 scattering amplitude. So we will have the vertex, contact term, plus the one loop.
Yes.
Right? So let's suppose we stop at one loop, okay? Just the bubble and the contact term, which will be the contribution to the 2 scattering.
Yes.
In this case, like, I mean, would you define the basis at each loop order?
Yes,
or
the basis can be defined, yes, indeed, at each loop order or at each even for each particle content, right? You can have according to the masses, you have the propagator, and the Bikov polynomial is once you go to Bikov representation, the polynomial depends on the masses, on the external kinematics, namely the Mandelstam invariance. Okay, so for each type of integral, or each family of integral, you have a Bikov polynomial. Of course, if in your problem it is sufficient to start from the most complex topology, of which, and the other eventually could be considered, the diagram could be considered as a subset. Okay, so it's sufficient to consider the most complicated diagram or the family of diagrams, and then for each of them you introduce the Bikov representation, and then you will be able to characterize, first of all, to count the number of master integral you need, and then to choose them. Okay.
Okay. So for instance, for the one loop contribution, you can have SUT channel. You would say that these are only one independent element.
No, you don't have only SUT because, okay, in the 2-to-2 scattering.
In the 2-to-2, I mean, just 2-to-2.
Yes. In a sense, no, then it really, you really need to count the cohomology group. It depends on the masses of the particle. In your example, presumably, it's just one bubble, one box, one triangle. No, in your case, it's a bubble. Okay,
just bubble with 4 vertices.
Then technically you may have 2 because you can have the bubble and the tadpole. Actually 3. You have 1 bubble and 2 tadpoles.
Right. Okay.
Although they are not diagram belonging to the process, they are integral that are useful to decompose, are needed to decompose your amplitude.
I see.
Thanks.
So you need to add them anyway. Okay. In that case,
Yeah,
this extra.
Yes, to complete the basis.
To complete the basis.
Because,
I see.
And then you can decompose any integral with the generic numerator, because in terms of this basis, using intersection number.
Okay, I see. Okay, thanks.
No, thanks to your question. So the way to compute intersection number also, it's maybe technically less known. I don't want you to go through the details, but the idea is to use Stokes theorem into a double, to write this surface integral. And in particular, allow me just to recall its basic structure. Namely, if you have the intersection number between two forms here, phi left and phi right, using Stokes theorem together with Cauchy generalized theorem, one is able to write this expression as a sum of residues in which the right form phi r remains as a spectator, and instead in the argument of the residue one needs to put this psi I, and psi I is the solution of this differential equation, namely nabla omega psi I equal to phi left. So phi left is used as a term to determine psi I, and then psi I is put into this formula to determine to evaluate the residue. And now you may say, okay, that solving this differential equation is generically complicated, is as complicated as evaluating the integral, but indeed what's known, or what's needed is not the full solution everywhere in the integration domain. Actually, what's needed owing to the residue formula is just the local solution around each poles. The poles here are the poles of omega, again the connection, the covariant derivative. So this can be engineered, and we have been developed. So this formula that I wrote here holds only for univariate case, but our goal was to extend this formula also to multivariate case. And I encourage you to see the similarity of this, let me say, non-trivial formula with respect to the two formula that I started from, okay, as a generalization of a discrete Fourier transform. So what we understood is that if we want to compute intersection number for complicated Feynman integral that depends on many denominators, since any denominator becomes an integration variable, we need to develop methods for evaluating n form. And that's what exactly in the last 3 years has been our main activity. In particular, what we started from was to consider the integral as an iterative integral with respect to each individual variable, and then essentially we decomposed all the internal integral in terms of master integral until reaching the final shell of the integration. Mathematicians would call this method vibration, we were calling it simply iterations. And without entering the technical details, again, in this iterative approach, we were able to show that if by induction, okay, if we know the intersection problem, and if we know the intersection number up to the n-1 level, then the last step can be obtained using the identity matrix in the n-1 level. So in this representation, again, you see the usefulness of the identity resolution matrix in order to compute the multivariate method. And there have been several tests of our method, starting from a mathematical function. Here I defined the Lauricella function that are characterized by this twist. One can determine the dimension of the cohomology simply counting the number of poles of the variable and the total number of integration domain. And we extending then this to the Feynman, to the evaluation of Feynman integrals, combining the idea of residue evaluated at each poles with the idea of polynomial division. This was a very nice intuition of Fontana-Peraro that we were able to combine also with the possibility of introducing special basis element, namely Dirac delta basis, which have a simpler intersection number, to simplify also the evaluation of the form. And this allows us to compute, for instance, one loop 6-point amplitude up to two loop 2-to-2 non-planar amplitude for massless particle as well as for massive particle. There has been in some recent interesting study in exploiting a special choice of the basis, which also may have an impact in minimizing or simplifying the computational load. And this was applied on one loop 6-point integral for massive scattering. And we combine this technology also with the generalized unitarity, namely decomposing integral on the cuts and then reconstructing the final result. The most advanced idea that so far we were able to produce was to promote the calculus of intersection number, or to combine the calculus of intersection number with the so-called companion matrix tensor algebra, namely working in a modular space so that all operations become operation among matrices, and skipping all the details, but essentially just communicating that for each operators we have a tensor-like representation. Then one could work with tensor algebra, and we were able to achieve what for us is considered an important milestone, which is the decomposition of two-loop 5-point integral for 2-to-3 massless scattering, for instance, in QCD, in terms of a basis of 62 master integral. And the coefficients of this decomposition can all be computed by intersection number. We went up to rank, now this is a bit outdated, up to rank 20, okay? We essentially means that we can have polynomial of rank 20 to be present in the differential form of this integral, and they can be easily decomposed. Or easily, in a sense, it takes 3 days, the decomposition in terms of this basis, but it was an important milestone also to show that the direct projection of an integral into a basis can be done alternatively to the integration by parts decomposition.
Have you also thought to do something similar for graviton scattering? Like, I don't know, something.
Yes, in a sense that
2 to 3 with two loop, like.
At the end of the day, yes, indeed. Let's say that a theory, so specifying so the method is rather general, and where the theory enters is in giving you clearly the vertex, the interaction vertex on the theory, and therefore the polynomial sitting, the rank of the polynomial that can generically appear in the numerator of diagram associated to an amplitude. So okay, we had also other method we propose other method which were new also for the mathematician. But what another message that I want to convey is that studying the Rham cohomology structure of theory of the integral also allow to exploit another duality that exists between integral and differential forms. So this is something that people that work with the GKZ system know very well. Namely, what's nice is that for twisted integral, okay, associated to this Euler-Mellin integral, it is possible from the form of the integrand to derive differential operator, here identified with this E, J, and box U. These are differential operator that annihilate the function. Okay, and one of the main important result of GKZ is that this differential operator can be seen as generators of a D-module, okay, associated to the Euler-Mellin integral. Now, the rank of the D-module, namely the number of independent differential operators, it's also related via an isomorphism to the dimension of the cohomology group. Okay, and it is indeed corresponding to the mixed volume of the Newton polytope associated to the twist, to the G function here characterized as GKZ. So this isomorphism can be exploited to derive a differential equation obeyed by differential operator in the same way in which one can build a differential operator for Feynman integral or for master form. And indeed, we proposed a method based on Macaulay metrics to derive these differential Pfaffian matrices. Okay, so beyond Feynman integral, actually, we started almost by joke with Sergio Cacciatori to apply this method to other integral that can be recognized as having a twisted period representation. And we started from the orthogonal polynomial relation. Okay, we know that in case of orthogonal polynomial, right, the integral of the product of orthogonal polynomial is essentially proportional to the delta function, and these orthogonal polynomials are indeed extremely interesting to investigate matrix element in quantum mechanics. So what we were able to apply this formula is to problem having this structure, and in particular we were luckily finding by experience that all these problems can be mapped or can be recognized as decomposition problem in terms of just one master integrals. Okay, so this formula written here can be derived simply as decomposing the original integral in terms of this master integral. Okay, and the coefficient in front of the decomposition can be obtained by by intersection number. So the idea is to recast the original integral as a twisted period integral, where the differential form is obtained by taking the product of the two polynomials Pn and Pm and together with the integration variable, and then identifying from the integration measure the twist. So here I have for Laguerre, Legendre, Chebyshev, Gegenbauer, and Hermite the corresponding twist, the number of master integral, which is always one except from the Hermite polynomial. This is the basis choice. Okay, having integrand 1, the integration measure dz is understood. This was the choice of the basis for the case of two master integral, and these are the symmetrics. Namely, for the case in which there is one master integral, the symmetry is just the self-intersection number of the master integral. Instead, for this case of two master integral, we have a basis 2 by 2 that we were able to diagonalize. In a sense, these two forms are diagonal. These are the expression of the master integral, and the orthogonality condition can be written in terms of can be computed in terms of intersection number. Okay, so and we apply then this to the harmonic oscillator in quantum mechanics, also mapped in terms of twisted period integral. For the harmonic oscillator, we could use exactly the same twist as the Hermite polynomial before, and we were able to rederive some results written in Landau book, or even the eigenvalue of the harmonic oscillator with the intersection number. And then we went on with the angular matrix element, in radial matrix element of the eigenfunction of the hydrogen atom, okay, specifying again the twist in this case, and deriving formula that also were written in the Landau book, again in terms of intersection number. And we went a bit on, okay, then even looking at the definition of the Green function, okay, we know that the Green function are generically defined as the ratio of two integrals, okay, the numerator and the denominator. But Weinzel observed nicely that this ratio can be also written as a decomposition formula, in which the numerator can be written as the Green function, namely the coefficient times the integral in the denominator, which can be considered as a master integral. And in this fashion, then the Green function can be interpreted as the coefficient of the decomposition. So the Green function itself is an intersection number, or can be computed by intersection number. And we indeed verified this in simple theories. For instance, this is phi to the fourth theory, in which the two-point correlation function, right, can be computed in terms of intersection number, specifying again a twist which is very similar to the one of the harmonic oscillator and the orthogonal polynomial, and the coefficient of decomposition can be found by intersection number, and they indeed give the resulted one aspects from basics of quantum field theory. But not only one can apply this method in perturbation theory, namely expanding around the coupling. We also tested a case in which the action is exact. In this case, the cohomology dimension from 2, okay, the number 2 become 4, so the cohomology dimension increase, but we can then decompose any integral in terms of basic master integral. And so, for instance, one can relate the two-point function and the four-point function, for instance, okay, finding relations among correlator functions. And we apply this also to Kontsevich-Witten tau function, reproducing a result known by Ikson-Zuber. And in the last few minutes, let me just tell that at this point we started one of our activities, with my collaborators, is really to try to identify problems that admit a twisted integral representation, and we were finding, for instance, in terms of Fourier integrals that can appear either in the analysis in the phenomenology of the computational wave, as well as in the deep inelastic scattering. And more recently, we applied it also to cosmological correlators, integrals that are so wave function that were defined by Arkaniamed, Benincasa, and Postnikov, can admit this twisted period representation. Here, for instance, there is a sample integral of a two-point correlator function at 3 levels, for which one can identify the number of master integral. This is the C matrix, for instance, and even computing the differential equation obeyed by the master integral. Everything in terms of intersection number. And lately, we were able to push the analysis to derive a first novel relation for the one loop correction to the point function. We even explored the one loop triangle correction, but in this case, we arrived up to the classification of the differential equation. The solution is still in progress. Okay, in the last really few minutes of your patient, I would like also to bridge this study of the Rham theory and twisted period integral into something that can be also can have connection with the neural network, and in particular with the so-called PIN, physics informed neural network. So trying at least only to give a hint, artificial neural network are essentially able to reproduce or to represent a simplification of special functions. For us, we are interested essentially in functions that obey differential equation. So in case of the existence of differential equation for our function, this differential equation can be used to minimize the error, okay, in the approximating error, which is known as loss. And in the representation of this physics informed neural network, it's just a little bit more articulated than the original one, but the bottom of the take-home message is that together with the sampling, okay, there is also the possibility to check, to verify the fulfillment of the differential equation, and this is much more stringent than just a standard neural network. This, for instance, is what happens if you consider a solution of a differential equation in standard neural network. So in the standard neural network, if you don't use the information about solving the equation, you can see that after a few tests, the behavior, which is indicated here by this red curve, start to deviate from the original wave shape. Instead, if you use in this PIN model, if you use in these green points are evaluated or checked the differential equation, you can see that it is sufficient just one training point. This is the red dot, and then the model it's able to approximate the function essentially over the full range of interest. And what we did, we extended this analysis also to solve systems of differential equation, which are more related to the problem of Feynman integrals, and in particular we saw it, or we applied to the case of hypergeometric integral, and in particular to elliptic function, which are functions that appear in the context of massive particle scattering, or even complicated black hole scattering. And here you see the green these are points, but okay, are the points where the differential equation is verified, and this is just a bunch of training point. You can see how well the neural network follow the analytic results. And in the literature, this idea was originally proposed by Zoya and collaborator. Here in Padova, we were able also to extend to some special elliptic integrals. This was a master thesis basis. So to conclude, allow me to say that all these investigation brought me to think back to Ampere's law. Okay, in a sense, when we want to compute the circulation of magnetic field, Ampere law tells that the circulation of the magnetic field is proportional to the current, and then the sign in front of the result depends on the orientation of the current with respect to the orientation of the surface. Now, this building block indeed can be used to determine the circulation of magnetic field, also in cases where the problem is much more complex. In fact, the result can be broken down in terms of elementary circuits, and the coefficient in front of this elementary circuit is indeed the sign that can be associated to the Gauss linking number, so the intersection number. So already from Ampere laws, we can decompose difficult integral in terms of basic integrals whose coefficients are completely determined by geometry, okay, namely by linking number. And that's what we have rediscovered in the context of Feynman integrals. Of course, in order to realize that, we need also to extend the concept of a linking number, which now we know is the intersection number between forms. And we were able to establish a one-to-one correspondence between concepts in quantum field theory, or computational quantum field theory, I should say, and twisted the Rham cohomology, in which a special role is played by the twist U, namely the function that characterizes the integral family. For Feynman integral is the Bigot polynomial, or any graph polynomial in any parametric representation you like. Would be semantic polynomial in Feynman parameter. For hypergeometric integral is really the kernel of the hypergeometric, is the product of the linear term. For Euler integral is the exponential function. So the twist is what characterizes the geometry and the analyticity of the integrals. And owing to this identification, then many concepts can be brought from quantum field theory back to math, or vice versa. So I like to conclude really that the Rham theory is not only interesting from the formal point of view of mathematics, but it provides for us a full mathematical framework to study the vector space structure of Feynman integral, and not only, but all integrals that admit a twisted period representation. The dimension of the vector space correspond to the number of master integral. The intersection number are the scalar products within this space. The key concept in the applicability of this mathematical framework is really the numerous, the different way one can establish isomorphism between various problems and a co-homology group. So this is really the triggered for us a very multidisciplinary investigation, in which concept of fundamental physics can be connected to geometry and to statistics. As a physicist, the quantity we compute are fluxes, okay? Some differential form going through a surface. Mathematicians like to call them period integral, and in statistics you have statistical moments. Okay, and so in this trifold scenario, then our research has been so far pinpointing between Feynman integral, the module, quantum mechanics, correlated function in cosmology, and also gluing method in N equal 4 super Young-Mills that I had no time, and more and more applications are coming out. So I really would like to conclude and thank for the patience. Sorry if I went a bit longer, saying that the amplitudes lab, namely the mathematical aspect of scattering amplitude, allowed us really to connect a different area of physics, also to in particular particle physics, which I originally belonged to, also to interesting area of gravitational waves, and in particular effective field theories. That is our key, is the key is the physics key of accessing new disciplines. And this research put us in touch with interesting mathematics, as well as now opening a bridge in modern calculus. So I'd like just to conclude with this sentence by Schwarz and Shapiro, and say that physics is a part of mathematics devoted to the calculation of integral of this form, integral of gx e to fx. A different branch of physics are distinguished by the range of the variable and the name used for the functions. So addressing a common math problem might be useful then to make progress all at once in different disciplines. Thank you very much for your attention.
Okay, thank you for your talk. Questions, please.
maybe in the meantime, I can just ask.
Yes, please.
Yeah. So, yeah, first of all, thank you very much, Pierpaolo. It's very nice, all this business of new business of new application of intersection theory, I would say, right? Because no one has thought about this before. And so,
Yeah.
for instance, what I missed was about this computation of the two-loop amplitude for 2 to 3 gluons. In that case, the computation is faster as compared to their methods or not?
No, no, it is not. It is not at the moment. Clearly, current methods available for the solution integration by parts identities have a long tradition of 40 years of research and many bright minds, also people in the audience that have been working on it. So, of course, in proposing this new framework, let's say I don't want to wait other 40 years to be able to develop a more efficient method. But I can say that the method in a way strongly depends on the method to evaluate intersection number. I don't think that the method that so far we have developed are the most ideal one. In particular, this iterative method, it's not efficient. But for us at the moment, it was also important to show the solidity as a proof of concept that this can be done. Therefore, if now, for instance, mathematicians come to us with better method to compute section number, then we would be extremely happy. Okay, part of our research is indeed devoted to develop new method, new also for the mathematician so far. But what can I say already as an advantage of this method can be seen is this higher rank decomposition. So namely how the method scales when the integral become more complicated. And we can observe that so the method based on intersection number scales much better than method on IBP. So IBP suffers when the power in the numerator becomes very high. And this happens, for instance, you mentioned gravity or supergravity, where owing to the self-interaction, the tensor rank can be high, or even in non-renormalizable theory. So in computing higher loop correction to effective field theory or supergravity, gravity and supergravity theory, then intersection theory, and then IBP are really at the current limit. And so therefore, the fact that the use of intersection number shows already an advantage, even if the method that we have is not ideal, for us is at least a motivation to insist and try to better understand the way to compute intersection numbers. Okay.
Okay, there is one question from chat, and I also would like to join to this question. This is a question about renormalization and diversion.
Maybe may I ask
yes,
it?
please, please make your comment.
Yeah, just the first question about the rule of regularization and renormalization in this integral, because maybe you discussed and I miss it, or no?
No, sorry, there was a leak in the communication. Can you repeat the question about regularization? You said yes.
If this decomposition also works
yes,
with the integrals which must be regularized.
So thank you. Indeed, okay. What I have said generically works for integral that are regularized, namely the gamma. In the gamma exponent, gamma is arbitrary exponent. Here d is an arbitrary complex number. Okay, so regularization, dimension regularization appears as a power in the twist. Now, interestingly, we were able also to lower this request, namely the Rham cohomology was also developed for so-called relative cohomology groups. And the difference between ordinary cohomology theory and relative cohomology theory is indeed in releasing this constraint on having arbitrary complex regulating parameter, and also to try to compute intersection number for a non-regulated integral. This is extremely interesting because it works. Okay, we can derive relations for non-regulated integrals, and as you know, this is extremely tempting from the formal point of view, because it may lead, okay, my words have to be taken with springs, but it is a method that could be eventually applied, for instance, at finite d, okay, directly. So instead of using the dimensional regularization, then taking the limit d to 4, 2, 3, the number of critical dimension of your problem, intersection number can be evaluated also directly for integral at finite dimension. And this is something interesting, while we know that integration by parts identities are not necessarily derived at finite. So one needs really to a careful way of solving the system of IBP if one want to extract those relations at directly at finite dimension. So there is a connection between the possibility of using these methods in a novel way. Okay, but yeah, I cannot say much more on that because experience is. We have not done a systematic study. Nevertheless, we have computed and we have tested our formalism directly at finite results. Namely, every time that we want to do this test, we first compute the integral for dimension, the intersection number for dimension regulated integral, and then take the limit and compare it with the algorithm that we have to compute the intersection number directly in finite dimension, and it's nice to see that they match.
Okay, more questions, please. I don't see more questions. Maybe I will ask you a question. You spoke here about theory where there are some simple propagator, just 1 p square plus m, that's all. What can you try to generalize your approach, for example, for 1 over n expansion, where there is a propagator of auxiliary field which has very non-standard form. Do you have any idea to generalize? So the general questions could be look like this. Can you generalize your approach for non-local propagator? There are several examples in physics where we need non-local propagator.
Yes, thank you for the question. This means that I failed in communicating the definition. In a sense, what I mean here is that, that generically the integral, Feynman integral in any theory can be first decomposed by a form factor decomposition in terms just of scalar integral. Okay, so this decomposition is totally arbitrary. So I gave. It's my fault. I gave these as understood. So the method that I proposed are not limited just to have 1 in the numerator, but what I gave as understood is that it's always possible to take my integral in my theory and first decompose in terms that have 1 in the numerator and then product of denominator with any power. And indeed, this power can be also negative. And if the power is negative, it means that the denominator is in the numerator. And therefore, this means that indeed I can have a generic polynomial in the numerator.
But so you assume that this is some kind of rational function, some polynomial, and could be more complicated function, like exponents, for example.
Yes, okay, let me, so the answer to, okay, as I said, this line of research is pretty new, but indeed in the application that we did late here, for instance, we were considering exponential function here, as well as here one can, there is an ongoing project by my PhD students using also logarithms. So indeed, the term that can appear in the numerator, indeed, it's not only just rational, but can be also something more articulated. But as I said, it's something new that we are testing.
Okay,
May I also
thank
ask a question?
Sure.
Please, ask.
Thank you. Yeah, thank you. Well, I had actually a related question. I think Irina asked you somewhat different, that you put there exponent of IQX. This we know how to treat. The question was if you have arbitrary function, like, for example, you have in string field theory, which will be not expandable, which you cannot decompose into separate, how to say, factors, simply because it's not factorized by Weierstrass product already, then the point, and it will not be as simple as just exponent of IQX. So the question is, are you ready to attack problem of some full propagator, which definitely will have some non-local factors, which you cannot decompose as you present?
So, okay, let me first say that although this exponential term may be, let me say, considered as trivial, allow me to say that the treatment of higher order correction involving them required, was not known in the literature. So it's really already something, at least from the particle physics point of view, this was already demanding. Now, we applied also our method to integral for string amplitudes, namely for twisting, in which they are related to Virasoro and Veneziano amplitude. That's also there we were able to identify master integral basis. Of course, whenever we change the form of the function, the master integral themselves can contain these functions. Okay, then we don't have simple scalar integral with 1 in the numerator. Okay, now I'm not sure. Right? I like to talk a posteriori. So what I can say, I have not attacked presumably the problem you and Irina have in mind. So at the moment I can only collect the proof of evidence of what we have been doing. But let me simply say that the mathematics on which this formalism is built, it's very general. Okay, so I cannot say for sure. Yes, one can apply to these formulas to the integral in mind, but eventually, if you show me one of these cases, maybe we can give it a try. And just for us, it's also an occasion to learn new areas.
Well, I can tell you what is exactly the mathematical difference. Mathematical difference will appear there compared to everything what you discussed, because, for example, if you take exponent of q squared,
yes,
you will have a real trouble to do Wick rotation, because you will have essential singularity in momentum space at infinity, which will forbid you a lot of known methods, and you will have to modify Feynman propagator, and this will require something new, and this was actually my question.
No, could be. I'm saying, namely, of course, if one consider new type of functions, then it means that, and if one is able to cast them or to recognize them as a twisted period integral, it means that one can still presumably identify a basis of function. In particular, one can define differential equations of differential equation for these functions. Okay, so that's, let me say, the ultimate goal. Namely, whenever there is a new function, right? How can one classify it? Well, one can classify trying to derive all possible relation this function obey, and eventually building a differential equation of this new function. It's a solution of. So I'm not saying that this method solves all the problem one may have. Up to now, seems to solve more problem than one was expecting. Integration by parts differential equation for Mastrolia to solve. And again, if one can give it a try, and see. Okay, of course, for the new type of function, then you don't have denominators, you don't have this rational function I applied my theory at, but the formalism itself essentially is based on Morse theory, and so and the Rham twisted cohomology. So if your functions are good, have good property to fall in this category, then yes, intersection theory can be applied. But again, it would be nice to see an example, and one can try. For instance, let me ask you a question. Do you already know if your function obey differential equations?
No, this is a simple function. Not, yes, I can, because I know the function and can write some differential equation, no problem.
Then by reverse engineering, I would tend to say yes, that it's a linear differential equation or non-linear differential equation.
I think, let me think a little bit.
If it is linear, then
we can write the linear equations with non-constant coefficients.
Non-constant coefficients, absolutely. Yeah, then okay, there is hope that one can cast also this integral in twisted period language.
And also, a more general questions. I don't see Branko Dragovic. Maybe he can. I expected such question from him. What about, where is the so-called p-adic field theory? In p-adic case, we have to integrate over p-adic variable, and this is widely used in different branch of statistical physics as well as field theory. It can be seen as a regularization of the usual case, but there are also some profound origin to consider such type of theory. Have you tried to generalize your theory for this p-adic field theory or not?
No, this is of course very interesting what you
This
are
could be
suggesting,
very
but
interesting development, I think.
absolutely, it is. Yeah, no, we didn't try to expand in this direction. Our main yes focus also is the area that we know more, in a sense, was the coming from the standard particle physics, and now we are exploring some more formal aspect, but we did not definitely reach this very interesting topic. No, we did not try that.
Okay. More questions, please. If not questions, maybe I will ask some kind of different questions. Of course, you know better as me that there is a program called Feynman calculus or something like this, a program which help us, which perform calculations in high energy physics or for all Feynman integrals. Do you expect that your activity can help to simplify this program, to make it work more faster? What is your impression?
Yes.
This is pure practical question, yes, I guess.
Yeah, indeed. Yes, this was also related to what Luca asked before. Yes, first of all, our program at the moment already helped and completed the so-called generalized unitarity-based approach. In particular, together with the intersection number unitarity cuts, one can really decompose the amplitude to collect the coefficient of all the master integral. And originally, the generalized unitarity method was not completely efficient in extracting the full tower of coefficients. So, and moreover, as said, this method indeed, we are developing it to try at a certain point to help people that use. There are people from your community like Volodya Smirnov that have developed the FIRE code based on integration by parts identities, and the idea is that with intersection theory one can really generate those sorts of identities in a different and more direct way. So theoretically, I think that the formalism is very clean. In practice, we need to improve the way we compute intersection number. So yes, our goal is really to help the development of multi-loop calculations for high energy theory, and not only, also in gravity at the moment, which seems to be extremely interesting, and it's important, right, for the description of the waveform models in the detection of a gravitational wave that may for sure may trigger new analysis from physics, astrophysics, and cosmology in the next few decades. So yes, but as I said, we need to develop more efficient algorithm for evaluating the section number.
Okay, thank you.
Thank you for the question.
More question? Please raise your hand if you want to ask something.
Well, we crossed 5:30, I guess, people.
No. Oh, if not, let's thank the speaker again for very interesting talk.
Thanks,
Very
Pierpaolo.
nice presentation.
No, I thank you. I really thank you.
Thank you. Thank
Thanks
you
a lot.
very much.
It was very nice. And Pierpaolo, if you can send us maybe the slides, we can upload them.
Okay. I will eventually send the link. A link